In this video, we set out to demonstrate that a tangent and a secant chord that intersect on a circle at the point of tangency, so this is our chord. If it were extended, it would be our secant line. This is our tangent line. Then the measure of the angle formed between them, is going to be half the measure of the intercepted arc. Remember, the intercepted arc is the central angle going from the center of the circle to the edges of the chord. Okay, so we are going to start with our givens. We have a circle at A. We have chord BC. Okay, and then we have a tangent line. We're going to make the definition that this right here is beta, corresponding to B, and that our central angle created from segments AB and AC is alpha. Okay, so we're given beta and alpha respectively. We're just going to call all of these given. Okay, our goal in this one is to demonstrate that beta is half of alpha, or that twice beta is alpha. Okay, so we start with the fact that this is a tangent line. We're again going to make use of the theorem that we haven't actually demonstrated, which is that the sum of internal angles in a triangle is 180 degrees. So we're now going to create gamma. Okay. And just to be clear, alpha is a different angle than beta, so it gets 2 arcs. Gamma is a different angle than either of them, so it gets 3 arcs. Okay. So we know that these two are congruent. These two angles, both gammas, are congruent based on our isosceles triangle theorem, which we stated in a much earlier video. Basically, if you recall, if two sides of a triangle are congruent, okay, which these are by the fact that they are radii, then the opposite angles to those will also be congruent. Okay, so we're going to state that just a proof of that. To be completely formal, that AB is congruent to AC, and therefore we have gamma 1 and gamma 2 as being congruent. Okay, basically by radii being equivalent, and then also from our isosceles theorem. Okay, which again we will demonstrate later in this chapter. Okay. We also make use of the total internal sum is 180 degrees. So we're going to write that 180 degrees must be equal to the measure of alpha plus 2 gamma, okay, which is the sum of the internal theorem from triangles. And we'll just write angle. You probably cannot write what I'm directly reading here, but it's just sum of internal triangle angle is 180. Okay. So now that we have that, we then use another theorem which we actually did prove earlier, which is that if this is a tangent line and this is a radius that connects at that point of tangency, which we were given, then we know that the angle between them is a right angle. Okay? So we know that gamma plus beta is a right angle, or 90 degrees. Okay? And this one, just to draw a quick line here, this one comes from our previous example of radius is tangent. The radius is perpendicular to the tangent at intersection, okay, which comes from a theorem that we just showed in an earlier video. Okay, so now that we have that, we're going to use both this equation and this one And we're going to say, okay, so gamma then must be equal to 90 minus beta. We're not actually interested in gamma, so we're going to substitute him in. So we have 180 equals alpha plus 2 times 90 minus beta, which comes from the transitive property. Okay. We then have, by simplification, 100 equals alpha plus 180 minus 2 beta. Okay. Through further simplification, the 180s go away. We add 2 beta to both sides, and we get 2 beta is equal to alpha, which is what we were interested in proving in the first place. If we divide by 2, we actually get the original form that we were looking for up here.